Hey, what's up, Calc 2 crew, and welcome back to the Daily Problem Sets. And today we're going to take a look at trigonometric substitution, which is, hey, this is Calc 2. This is what we're doing. Usually I think we take a look at maybe 3 of these problems. I think for trigonometric substitution, we're going to have to cut it down to just 2. These can be lengthy problems, but let's see if we can take a look at a couple of them, and I'll leave you with one to try on your own. But as with any of these, make sure you're viewing the lecture material before taking a look. If you want, go ahead and pause the video, try this problem out, then resume, take a look at it with me, and we'll make sure that we're good to go. But let's go ahead and take a look at this first one. Here we have the antiderivative of x to the 5th divided by the square root of x squared plus 4 with respect to x. Now, you should already be comfortable with these common forms. We're looking at the square root to make our judgment here. And since we have something of the form square root of x squared plus a squared, square root of x squared plus a squared, then we want to do the substitution, let x be equal to a tangent theta. And in this case, we have x squared plus 4, so square root of x squared plus 4. 4 can be written as 2 squared. So the substitution that we want is letting x be equal to 2 tangent theta. Now, a big oversight that I see is that we have to make sure that we're also taking the derivative of this because we have to replace dx. Now, I don't think you're going to make a mistake because you're the best. You got it going on. You got that cup of coffee. You're awake. You're alert. You're a genius. But if I see a mistake, more often than not, it's just replacing dx with d theta carelessly. I need to do that, make no mistake about it, but in order to do that, I have to use the derivative. I can't just swap out dx and d theta. That's not going to work unless I have a very simple direct relationship between them. In fact, we can see the relationship between x and theta here is quite complicated, so we have to honor that by taking the derivative. We'd say the derivative of x is dx. And then 2 comes along, but the derivative of tangent theta is secant squared theta d theta. And this is an okay substitution to make. These are true statements. So let's go here and start swapping out. Got the antiderivative of, instead of x to the 5th, that's going to be 2 tangent theta all to the 5th, divided by square root of, I want x squared, so that's 2 tangent theta squared, and then plus 4 is under there as well. And then the dx, I can replace dx, but I have to replace it not just with d theta. There's a lot more than that. I can replace it with 2 secant squared theta d theta. And it's looking good. Everything's looking really good. Now, I have some work to do. I'm not ready to just integrate this. I have to sort of unravel it first a bit. So let's go ahead and expand this out. 2 to the 5th and then tangent to the 5th is really what we have. So 2 to the 5th, tangent to the power of 5 of theta. And then while I'm at it, I can bring this other 2 up there. I could join it with the 2 to the 5th, but I'm going to wait on that. And I also have a secant squared theta. I can write my d theta out to the side. And under the square root, I could say, well, 2 tangent theta, if I square it, gives me a 4 tangent squared theta plus 4. But I'd like to continue working from here. So what else can I do? Well, little steps, right? Here I have 2 to the 5th, tangent to the 5th theta, times 2, times secant squared theta, but the d theta over there, all divided by, here I have square root of, let me factor the 4 out, and I could say 4 times, in parentheses, tangent squared of theta plus 1. And this is going to be helpful, right? This is what I'm going to need to work with in just a bit. Now I can use the product property of the radical. That means I can split this up into, instead of the square root of a product, the product of the square roots. So I'll write that rule right up above. Square root of a times b is equal to square root of a times square root of b. But what that means is I can say this is the antiderivative of 2 to the 5th times tangent to the fifth of theta times 2 times secant squared theta divided by, I'll get the d theta over there, square root of 4, which is going to give me 2, and then square root of tangent squared plus 1. Okay, so looking good so far. Now there's a few things to mention. First of all, the 2 on top and the 2 on bottom are going to cancel. And in the denominator, the reason why we do this trigonometric substitution is so that I can get rid of that nasty square root expression in the original integrand. Now things are very different. The trade-off is that now I have to work with a trigonometric integral. So it's like moving back into 7.2, the previous section. But how can I get rid of that square root symbol? Well, remember your Pythagorean identities. And I'll be a bit lazy with my notation here. That's not to anger anyone, but just for shorthand. Sine squared of x plus cosine squared of x equals 1. And if I divide everything by a cosine squared, then I'm going to get another identity, tangent squared of x plus 1 equals, and then 1 over cosine squared gives me secant squared of x. And these are those identities that we're comfortable with and familiar with. And what I can do is I can replace tangent squared of theta plus 1 with secant squared of theta. So if I go back here, let me get the yellow chalk. I have the antiderivative of 2 to the fifth, what is that, 32? Let me just jot that down. Tangent to the fifth theta, secant squared theta, all divided by square root of. Now tangent squared plus 1 is going to give me secant squared of theta, d theta. Now this is where I can start making some pivotal moves. I can say the square root of secant squared is secant. Now that's sort of a bit of, it feels funny saying that. There are restrictions that we place on theta when we do trigonometric substitution. I'm not trying to be sketchy. I'm not trying to, be hand wavy or anything like that. But we do say the square root of secant squared is secant. If you want to argue with me about it, then find me on the online chat in the discussion board, and I'm ready. I'm ready. But we'll say it's secant theta for right now, and I can cancel the secant squared on top with the secant on bottom and reduce this a bit. So what do we have? We have the antiderivative of 32 times tangent to the fifth of theta times secant of theta d theta, and nothing in the denominator anymore. We're done with the fraction in this one. Okay, feels like we've done a lot of work. I've been yelling at the computer screen for a bit now. But where are we? Right now, we're at a trigonometric integral. So now we're in another problem. These, like I said, these are lengthy problems. It's sort of many problems within one. So this is a good test of what we've been learning so far in the semester. Now what I want to do is I want to think about how I can, proceed with this trigonometric integral. And I want to think back to the different sort of steps that we took. When I look at this, I see tangents and secants. I want to remember derivatives of tangents and secants. We said the derivative of tangent is secant squared. And we said the derivative, scooch down here, derivative of secant is secant tangent. And it looks like the only thing I really have to work with here is this odd power on tangent. So what I would do if it were me, if I were you, got a friend here to help. It's my cat Spumoni. I would break up tangent to the fifth as tangent to the fourth times tangent. And let me write the other tangent at the end. We'll say secant theta, tangent theta, d theta. So I still have my tangent to the fifth, but I split it up a bit. And now, now I want to rewrite the tangent to the fourth as, you got it, tangent squared squared. Yes. And now I'm still going with it. Now I can replace tangent squared with secant squared minus 1. So this identity right up here, our Pythagorean identity in blue, I can solve it for tangent squared by just subtracting 1 over. So tangent squared is secant squared minus 1. So here we'll say secant squared theta minus 1, quantity squared, times secant theta, tangent theta, d theta. And I feel good about this. I feel good about this because now I can work with a u substitution. I can say, let u be equal to secant theta, where du is secant theta, tangent theta, d theta. And that all gets taken care of in the substitution. And this gives me the integral of 32 times, in parentheses, here I have u squared minus 1 squared times du. So I'm really focusing on this as a trig integral now. So we got to be awake and alert for these trigonometric substitutions. Now I can expand this out. So this becomes the integral of 32 times, and then if I FOIL, u squared times u squared is u to the 4th. Minus u squared combines the outer and inner terms to give minus 2u squared, and then minus 1 times minus 1 is plus 1. I still haven't integrated, but now I can integrate. We'll say 32 comes along as the coefficient. But if we integrate u to the 4th, we get u to the 5th over 5. Minus 2, we integrate u squared, gives us u cubed over 3. And then here, if we integrate 1, gives us u. And then don't forget that constant of integration. But now we can back substitute. We said u was secant theta. So we're going to back substitute. So here I have 32, leaving that factored in front. Let me bring the coefficients out inside the parentheses too. That's 1/5. Instead of u to the power of 5, I have secant to the 5th of theta. Minus 2/3. Instead of u cubed, though, I have secant cubed theta. And then plus u, but u is secant theta. And then I don't want to forget about my constant, plus c. It feels like we're done, but with trigonometric substitution, we're never done. Let's be honest. It's never quite done. We still have to get everything back in terms of the original mama variable. And that variable was x. I got theta. I got trig functions and theta. That's not what we want to leave for our answer. How do we do that? Got to get that right triangle. So I need to go all the way back to my original substitution, x equals 2 tangent theta. And I have to build a right triangle and work with right triangle trigonometry. So x equals 2 tangent theta. You sort of, I'll use this space here. X equals 2 tangent theta. And I want to solve it for the trig function. So I'm going to divide 2. Say x over 2 equals tangent theta. Now, you've taken a pre-calculus course. You've talked about trigonometry before. If I say something like SOHCAHTOA, is that going to make anybody uncomfortable? It's not going to piss you off or anything. SOHCAHTOA. That's, maybe you've heard it differently. Let me know. I don't know if it means anything to you. I just like to say it, SOHCAHTOA. If you've heard SOHCAHTOA before, let me know. If you've never heard SOHCAHTOA before ever, let me know. I want to know. But this is the TOA of SOHCAHTOA, which means that tangent is the opposite over adjacent. It's just a little mnemonic device, SOHCAHTOA, for sine, cosine, and tangent. Let you know how the right triangle trigonometry is going to look. And I want to draw my obligatory right triangle. It doesn't matter how it looks. Mine always look the same. I draw them like this. Here's my right angle. Here's my little angle theta. They don't have to be special. And everything is relative to angle theta. When I say the opposite side and the adjacent side, those are not hypotenuses. Opposite and adjacent referring to opposite of theta, adjacent to theta. The opposite side is x, the adjacent side is 2, and I can use Pythagorean's theorem to find the missing leg, which in this case is the hypotenuse. So what would that be? Well, it'd be x squared plus 2 squared, and then the square root of that sum. So I want the square root of x squared plus 2 squared, or the square root of x squared plus 4. Now, something we should maybe be thinking about lightly is that whenever I build this last leg of the right triangle, it should be a familiar expression. In fact, it should be the motivating expression for the substitution that we went with. So that missing leg was square root of x squared plus 4. That's familiar. That was the piece of the integrand that pushed us to make the substitution that we made. So that's important, right? That's important here. But so there, now we have our, let me see if I can like box it. We have our right triangle to work with. And what I want to do is I want to use this to make my replacements. Now in this example, all I have are secants. So I need to be replacing secants. And what is secant? Well, secant of theta is 1 over cosine theta. And what is cosine theta? That's the ka of SOHCAHTOA. That's the adjacent over hypotenuse. So 1 over cosine flips it, so it's now the hypotenuse over adjacent. And I know what these pieces are. The hypotenuse is square root of x squared plus 4. And the adjacent side was 2. So this is what secant of theta is. And this is my final replacement that I need to make. So we'll say, okay, so I have 32 in front. And I have 1/5 times secant to the power of 5. But what is secant? Secant is radical x squared plus 4 over 2. And then I have minus 2/3. And then I have secant cubed. But what is secant? That's radical x squared plus 4, and then divided by 2. And then plus secant theta. We said secant theta is square root of x squared plus 4 divided by 2. And I don't want to forget my constant plus c. So this is my final answer now. So these do actually end. I was kind of joking. Seems like they take forever, but it's just a bit of work, a labor of love, but definitely worth it. Trigonometric substitution. And we have everything back in terms of the original variable. Not exactly a pretty looking response, but this is what we get, and we're happy with it. Let's take a look at one more of these, and then I'll introduce a problem for you to try out on your own. Let me know how you're working with it, and yeah, we can talk about it certainly. Let's take a look at this one, the antiderivative of the square root of 1 minus 25x squared. Now, of all the different forms that we have, this one doesn't quite match perfectly with any of them. But what it would like to be, or would like to mimic, is the square root of a squared minus x squared, which would lead us to making a substitution of x equals a sine theta. However, it's not quite ready for that yet. So we're going to have to modify this. And I'm going to do this sort of separately to the side, and then I'm going to return back to the original expression because I think it's a bit easier. However, the modifications that we're going to make aren't going to really change anything except for cosmetically. So here we have the square root of 1 minus 25x squared. And this is just so I can figure out what a is. You might be able to tell what a is already by inspection. If you're not able to, that's why I'm doing this. I'm going to replace a with 25 over 25. The real issue, or what I'm trying to do, is I'm trying to get rid of this coefficient on x squared. And I want to factor it out. In order to do that, I want to make sure that I'm factoring out of everything. I can't just factor selectively. So I'm going to have to rewrite 1 as 25 divided by 25, which is, it's the number 1. It's just a new representation of it. Then minus 25x squared. And now I can factor a 25 out under the radical still. And I'm left with, in parentheses, 1 over 25 minus x squared. So it's starting to look better. And if I want to return back, I can always distribute back through under the radical. Now what I can do is I can use the product property of the radical and say square root of 25 times the square root of 1 over 25 minus x squared. The square root of 25 is just a number, it's 5, so I don't even really care about it, to be honest. But for the rest of this, I can think of 1 over 25. 1 over 25 is 1/5 squared. and then minus x squared, and that's under the radical. Now, I said I was just doing this to figure out what a is cosmetically. If we remember, we wanted square root of a squared minus x squared to help elicit the substitution x is a sine theta. And we can see now that a is actually supposed to be 1/5. So if you could already tell by looking at it, that's good. I like it a lot. But if not, we modified to show that. So now we know what our substitution should look like. So let's go ahead and mention it. We'll say, okay, our substitution should be, let x be equal to 1/5 sine theta. I also need the derivative. Get it right out of the way. As soon as you know what your substitution is, find the derivative. Dx is 1/5 cosine theta d theta. And I want to make these substitutions. Now I said you can plug into this version that we have right here. We've just modified it, but it's still the same thing essentially. It's just different algebraically, cosmetically I said. But I prefer to plug into the original. I think it just makes it a bit easier. It's a bit cleaner. So let me plug back into the original, because all I wanted to do this work for was just to find out what a was, just to figure out what my substitution should be. Now that I know the substitution, I can go back to the original. So that was the antiderivative of square root of 1 minus 25x squared. But I'm replacing the x, so the 25 and then the x squared, I'm replacing the x with a 1/5 sine theta. And I have to replace the dx as well. Dx gets replaced with 1/5 cosine theta d theta. Nice. And we can start working with this. So what is this going to do? Well, here I have the antiderivative of the square root of 1 minus 25 times 1/5 times 1/5 is 1 over 25. Sine times sine is sine squared theta, and then times 1/5 cosine theta d theta. And a little bit more. This one actually turns out pretty nice, I think, because we have antiderivative of the square root of 1 minus, here the 25's cancel, so it's just 1 minus sine squared theta under that square root, times 1/5 cosine theta d theta. And now I can work with America's favorite trigonometric identity. You know that sine squared plus cosine squared is equal to 1. So then if I subtract over, we say cosine squared is equal to 1 minus sine squared. So now I can go here and write this as the antiderivative of the square root of 1 minus sine squared theta is cosine squared theta, and then times 1/5 cosine theta d theta, which this is going to give me the antiderivative of cosine theta times 1/5 times cosine theta d theta, or the moment we've been waiting for, I can say that this is 1/5 antiderivative of cosine squared theta d theta. Feels like we've done a lot of work, right? Well, now we're at the point where we have a trig integral. So we're back in the previous section. Now we're thinking, how can I integrate this trig integral? This is an even power, and it's just one of the functions. I just have cosine squared. So in order to do this, in order to integrate, we're going to need to work with an identity. So the identity that I would like to use is that cosine squared is 1/2 quantity 1 plus cosine 2x. I'm using it for theta, of course. I'm going to use this identity. I'm going to make these replacements. So here I'm going to have 1/5, and then I'm integrating cosine squared, but I'm replacing cosine squared with 1/2 quantity 1 plus cosine 2 theta, and then with respect to theta. And here I can bring the 1/2 out to join the 1/5, so that's going to give me 1 over 10. And then I can start integrating this 1 plus cosine 2 theta with respect to theta. And we'd say, okay, so 1 over 10 is in front. If I integrate 1 with respect to theta, it gives me theta. If I integrate cosine, it gives me positive sine. Remember, we're not talking about derivatives, we're talking about antiderivatives. But since it's cosine of 2 theta, it's going to be a little bit different. And you could use a small substitution to show this. I think we see it enough where it's reasonable just to kind of commit it to memory that when I integrate cosine of 2 theta, it's going to give me sine of 2 theta divided by 2. But the way you could show that if you're not quite sure where it comes from, it's really from a small u substitution. Let u be 2 theta, and then you can go from there. And then since I've actually integrated at this stage, I don't want to forget my constant, plus c. You would think that we would be ready for the final steps, but there's one more step before the final steps. There's a lot of steps, in case you haven't noticed. The issue is that although I can talk about theta and all of the trigonometry with theta, I can't tell you anything about 2 theta. That's a problem. I want to get this in terms of theta and not in terms of 2 theta. So we're going to need another popular trig identity. That identity is sine of 2x is 2 sine x cosine x. Or we can in fact just divide by 2 and say that sine of 2x divided by 2 is equal to sine of x cosine x. So this is the identity that I want to use now. Sine of 2x over 2 is equal to sine of x cosine x, which allows me to just quickly rewrite this. I can say that this gives me 1 over 10 times, in parentheses, theta, plus this is going to give me sine theta cosine theta, and then plus my constant c. Now everything's in terms of theta and a function of theta and not a function of 2 theta. Now we're ready to start talking about our right triangle trigonometry. Let's go back. We always go back to our substitution that we made. This was x equals 1/5 sine theta. So x equals 1/5 sine theta. And I want to get this in terms of just the trig function, so I should multiply 5 over. So we say 5x is equal to sine theta. I really want to see this as a fraction, though. 5x isn't a fraction, so we just use that classic trick, divide by 1. 5x over 1 is sine theta. And we want to remember SOHCAHTOA, and this is the so. So it says that sine is the opposite over hypotenuse. And now I can use this information to draw out my right triangle. Mine always look the same. There's my right angle, there's my angle theta. I know the opposite side is 5x. I know the hypotenuse is 1. And I want to find the adjacent side. So we use Pythagorean's theorem to do that. We would say, well, if I square the 1 and then subtract away the square of the 5x and then square root that difference, it would be solving for this. Or the unknown, the adjacent side squared plus the 5x squared should be equal to the 1 squared. And we'd solve from there. So that gives me square root of, I would want to square the hypotenuse, 1 squared is 1. I would want to square this opposite side, which is 25x squared, and subtract that away. So I get this radical 1 minus 25x squared, solving for that missing adjacent side. Remember, we said it's important to find this and then kind of check. I want to make sure I didn't make an error anyway. Along the way, this should be a familiar term. If I go all the way back, remember this was the motivating term that brought about the substitution that we chose. Now what am I replacing? I'm replacing theta, sine theta, and cosine theta. Now I already know what sine of theta is. Sine of theta is 5x. I said that early on. So I already knew that. I didn't need to do anything to find that. Cosine, however, remember that's the ka from SOHCAHTOA, that's the adjacent over the hypotenuse. And here the adjacent side we solved for as radical 1 minus 25x squared. And then over the hypotenuse is 1. So that just gives me square root of 1 minus 25x squared for cosine theta. And what about for theta? So I can replace sine theta with 5x, cosine theta with radical 1 minus 25x squared. Replacing theta actually isn't so bad. We could say since sine of theta is equal to 5x, then if I apply sine inverse on both sides, sine inverse of sine theta is equal to sine inverse of 5x. And we would say sine inverse of theta is theta equals sine inverse of 5x. Or I usually prefer to write arc sine. I think sine inverse can be sometimes confused with reciprocals, which it is not. If you want to use sine inverse, then use arc sine instead. So I could say that, well, theta is just the sine inverse of 5x, or that theta is just the arc sine of 5x, which isn't really too much work. It's just kind of finding an appropriate substitution for it. So now I can make all these replacements safely. So I'd say we had 1 over 10. Then in the parentheses, we had theta first, which we can replace with arc sine of 5x, plus sine theta times cosine theta. We said sine theta was 5x. We said cosine theta was square root of 1 minus 25x squared. We can close it and then get our constant on there. So we replaced it. Now we're back in terms of that original variable, which was x. Everything is looking great. There's our final answer. Give it the star. Now, these are lengthy problems, so we have this next one that we're not going to look at together, but I encourage you strongly to give it a shot. This is the third type of trigonometric substitution. We saw the other two, there's 3 of them in total, so this is going to be the other type of substitution. Give it a shot. The antiderivative of the square root of x squared minus 9 all over x cubed dx. You can do it. You were born for trigonometric substitution. I believe in you. The real question is, do you believe in you? Yes, you do. But so let me know what you're getting for this. Let me know how it's working out. Talk to me. Got an extra sheet there for you. We're moving on to talk about some PFD, partial fraction decomposition. Again, you should have already had a chance to check out the lecture video on this. We're just here having a party doing our extra problem sets. Let's take a look at this antiderivative of x minus 8 over x squared minus 7x plus 10. See what we can do with this. We want to start by factoring, right? Since the degree of the numerator is less than the degree of the denominator, I can go ahead and start right away trying to factor the denominator. And I don't even want to worry about integration yet. I'm going to have to integrate, make no mistake about it. That's why I'm here. That's what it tells me to do. But I want to focus on the fraction at first, just the function. I can factor the denominator, x minus 2, x minus 5, and this is going to be a case 1 partial fraction decomposition, which I can split up into the sum of 2 smaller fractions, one with x minus 2 in the denominator, another with x minus 5 in the denominator, and each with arbitrary constants on top, a and b. And I want to solve for what those have to be, so hopefully they don't stay arbitrary, right? I want to know what they should be. Now, from here, what I like to do is I like to build back the common denominator. So this a over x minus 2 really needs to be multiplied by x minus 5 over x minus 5. B over x minus 5 needs to be multiplied by x minus 2 over x minus 2. And from here, we're going to be able to have well, let me go ahead and show. So we have x minus 8 over x minus 2 times x minus 5 equals, here we're going to get one big fraction, superfraction, and the denominator is going to be that common denominator, x minus 2 times x minus 5. The numerator is going to be a little bit complicated. It's a times x minus 5, and then plus b times x minus 2. Now, since we're hoping these two fractions are equal, and I can tell right away by inspection that the denominators are the same, then the numerators must be equal, is really what we turn our attention to. So we'd say that x minus 8 must be equal to a times x minus 5 plus b times x minus 2. And I would like to expand this out. There's some other sort of ad hoc methods you could use to solve for a and b that I kind of disagree with because they flirt a bit too much with singularities. I don't like that. But we can work with a system of equations is what I like to do. Let me know if you like systems of equations too. I want to expand the right-hand side. So we'll say x minus 8 is equal to ax minus 5a plus bx minus 2b, or not to be? That is the question. A little Shakespeare for you. And I want to set the like terms, the like coefficients equal. So x's, I got some x's. I got an x on the left. I got 1x. 1x should be equal to, on the right, I have ax plus bx. Just focus on the coefficients. So that's a plus b. So the 1 on the 1x should be equal to the a plus b on the a plus bx. And if it helps, think about just writing those together. We would say 1x minus 8 equals, I can write this as a plus b parentheses times x, and then minus 5a minus 2b. So I'm saying the 1 in front of the x should be equal to the a plus b in front of the x if I group it. And then I also have the constant terms. I got a negative 8 on the left. My constants on the right that don't have any x's are negative 5a minus 2b. And this gives me a system of equations. I have two equations, two unknowns, and I want to solve this. If you haven't solved systems of equations before, I think the easiest way to jump into it is working with a substitution method. So I'm going to go to the first equation, and I'm going to solve it for a. That means a is equal to 1 minus b. And I'm going to plug this into the other equation. I'm going to say negative 8 equals negative 5 times, instead of a, I'm going to replace that with 1 minus b minus 2b. So that negative 8 is equal to negative 5, and then plus 5b, since I'm distributing, and then minus 2b. I can add 5 over, so that gives me negative 8 plus 5 is going to give me negative 3, equals 5b minus 2b is 3b. So then b is equal to negative 1. And a is equal to 1 minus b. So a is equal to 1 minus negative 1. So that's 1 plus 1, so a is 2. So now I know b is negative 1 and a is 2. So this is important. This is important. So this tells me that my original fraction, x minus 8, divided by x minus 2 times x minus 5 is equal to, we said a over x minus 2 plus b over x minus 5. We can see that in the yellow. A over x minus 2 plus b over x minus 5. And we know that a is 2 and b is negative 1. Now, what did I want to do? I wanted to integrate this original rational function. But instead of integrating this, which is very difficult to do, I would prefer to integrate its partial fraction decomposition. So we integrate these smaller fractions instead. That's why we go through this work. And this isn't so bad to integrate. We would say integrating 2 over x minus 2, well, 2 comes along as the coefficient, but if I integrate 1 over x minus 2, gives me natural log of x minus 2, should be natural log absolute value of x minus 2, just to clarify there. And then here I can bring this minus sign out, the minus 1, and if I integrate 1 over x minus 5, gives me natural log absolute value of x minus 5. And then I don't want to forget my constant, of course. And so they were able to successfully integrate the smaller fractions. Hey, and there we go. Let's see if we can't take a look at a couple more of these partial fraction decompositions. Here we'd like to integrate 9 divided by x minus 2 and then x plus 1 squared. This is going to be a case 2 partial fraction decomposition where we have linear factors in the bottom, but in fact that x plus 1 is being squared, so it has multiplicity 2. So what do we do in that case? Well, again, we focus first on just the fraction, because we have to address that. Now this x minus 2 term, that's really a case 1. So I can just deal with that like I did previously. I could say, well, that's a over x minus 2. But here, for the x plus 1 squared, we have to build up to that multiplicity. So I want to start with x plus 1, and then I want to get to x plus 1 squared. And on top, I'm going to want constants for each of these. With case 2, it's still constants in the numerator. So I want b over x plus 1, and then c over x plus 1 squared. And I would continue this until I got to the multiplicity of that repeated linear factor. So if it was, let's say, an x plus 1 to the 4th, I would need to continue. I would need d over x plus 1 cubed, and then e over x plus 1 to the 4th, right, so on and so forth until I get to where I'm headed. But always with constants on top in this case. This is a case 2. Now, from here, it's really the same as what we did previously. I want to build back the common denominator. So what is the x minus 2 missing? It's missing an x plus 1 squared. So I multiply by x plus 1 squared over x plus 1 squared. The b over x plus 1 is missing another x plus 1 and an x minus 2. Well, I'll cut off my plus sign, but I like to live dangerously. I feel no regret for that. And the x plus 1 squared, that's only missing x minus 2 on top and bottom. And now I'm going to skip over. You can hopefully notice that all the denominators are the same on the right, so we can write it as one big superfraction with that same denominator. It's equal to the fraction on the left, which has the same denominator. So we focus on the numerators, and we would say that 9 better be equal to a times x plus 1 squared plus b times, that was x minus 2 times x plus 1, plus c times x minus 2. And I should expand this out. We'll say 9 is equal to a times, and then x plus 1, if I square it, gives me x squared plus 2x plus 1, plus b times x minus 2 times x plus 1. If I FOIL this, I get x squared minus 2x plus x is minus x. Minus 2 times 1 is minus 2. And then plus c times x minus 2. And then I would want to expand out on the right-hand side. Maybe let me rewrite the left-hand side kind of a bit funny. It's just 9. So I could say 0x squared, because it's not there, plus 0x, because it's not there, plus 9 equals, and now if I start distributing, ax squared plus 2ax plus a plus bx squared minus bx minus 2b plus cx minus 2c. And now I can start setting these like parts equal. Tell me about the x squareds. On the left, I've got no x squareds. It was just a 9, so that's 0 on the left. What about on the right? I got an ax squared, I got a bx squared. I want to talk about the coefficients, so that's a plus b. Let's talk about x. What do I got on the left? No x's. That's a 0x. So 0 on the left. What about on the right? I have 2ax minus bx, cx. So just the coefficients, that's 2a minus b plus c. And what about the constant terms? Well, on the left, I do have a constant. It's the only thing I have. It's 9. And then on the right, I have a minus 2b minus 2c. And I can start working from here. So we'd say, okay, well, let's see if we can start making some substitutions. Now I can start with the first equation. If a plus b is equal to 0, I could solve for b and say that b is equal to negative a. Now I can go into the second equation and say that 0 is equal to 2a minus b, but b is negative a, plus c. So what does that tell me? Well, that tells me that 0 is equal to 2a plus c, or that 0 is equal to 3a plus c, or solving for c now, that c is equal to negative 3a. So I know that b is equal to negative a, c is equal to negative 3a, And I can go into that third and final equation, and I can get everything in terms of a and solve for a and then backtrack. So we'll say, okay, so then 9 is equal to a minus 2 times b, but b is negative a, minus 2 times c, but c is negative 3a. What is this going to become? Well, I have 9 is equal to a plus 2a plus 6a, which means that 9 is equal to 6, 7, 8, 9a. So then a must be 1. Well, if a is 1, then b should be negative 1. And c should be negative 3. So I in fact know a is 1, b is negative 1, c is negative 3. So now I can go back to my partial fraction decomposition. I can say, well, it's a over x minus 2. A over x minus 2. We said a was 1. Plus b over x plus 1. We had b over x plus 1. And b is negative 1. And then c over x plus 1 squared. We said c is negative 3. And this is the same as the fraction that we started with, just broken into smaller fractions. So this is what I want to integrate. This is what I want to integrate. We can go through the integration now. So here, the first two are pretty straightforward. It's just going to produce logarithmic functions. If I integrate 1 over x minus 2, gives me natural log absolute value of x minus 2, minus, if I integrate 1 over x plus 1, gives me natural log absolute value of x plus 1. But here for this third one, really what we're thinking about is a substitution. Think about this as the antiderivative of negative 3 times x plus 1 to the power of minus 2 with respect to x. And really there's a small substitution going on here. We're saying u is equal to x plus 1, du is dx. So then we're getting negative 3 times the antiderivative of u to the power of minus 2 du, which gives me negative 3 u to the minus 1 over minus 1, plus my constant c. And this resolves to give me positive 3, but then divided by u if I rewrite it. And then I want to back substitute. And I can do that down here with the rest of my work. So this would give me 3 divided by u, but u is x plus 1. And plus my constant c. So that last one didn't give me anything logarithmic, of course. Still, though, not so bad. I think we got some time for one more. What do you say? PFD, partial fraction decomposition. This is, here we have 10 over x minus 1, and then x squared plus 4. Now this is fully factored. I can't factor it anymore, and this is going to be a case 3 partial fraction decomposition. So I can take, I just want to focus on the fraction at first. And this very first term, the x minus 1, is really a case 1, so I can just do a over x minus 1. But for this x squared plus 4, I cannot factor it. It's in fact irreducible. It's an irreducible quadratic. I can't factor it. Since I can't factor it, I'm going to have to work with it as is. And it's not linear. It's not of any multiplicity. It's a quadratic that I cannot factor into something linear. So what I would do, I want you to notice that this is different than if I had something like x plus 4 quantity squared. That would be something that's linear with multiplicity. This is not linear, this is quadratic and cannot be factored. So what I have to do in this case is I can't get away with a constant on top. I need something of 1 degree less on top. So I need something linear on top. So I need some generic linear term, bx plus c. And this is how my partial fraction decomposition is going to look. Now I can work from here, same as always, right? I build back the common denominator. A over x minus 1 is missing x squared plus 4 over x squared plus 4. And the bx plus c over x squared plus 4 is missing x minus 1 over x minus 1. Now we get that common denominator back. We focus on the numerators. So we'd say 10 is equal to a times x squared plus 4 plus bx plus c in parentheses times x minus 1. We would expand this out. 10 is equal to ax squared plus 4a plus, here we have bx squared minus bx plus cx minus c. We want to start setting like parts equal. X squared terms, I got none of them on the left. That's a 0 for x squared. But then over here on the right, I have ax squared plus bx squared, just the coefficients, a plus b. X terms, got any x's on the left? No, I do not. That is a 0x. On the right, I have negative bx plus cx. Just focus on the coefficients, negative b plus c. Constant on the left, I got it, it's a 10. On the right, do I got any constants? I do, 4a minus c. So this gives me my system of equations to work with, 3 equations, 3 unknowns. And we can start working with it. So here, if I go ahead, I'd say, well, here I could solve for b, for example. We could say b is equal to negative a. If I go into the second equation here, I could say 0 is equal to negative b plus c, which means that c is equal to b. But since I know that b is equal to negative a, that c is equal to negative a then, since c and b are the same. And now I can go into this last equation and say, well, 10 is equal to 4a minus c, but c is the same as minus a. So I get 10 is equal to 4a minus negative a, which is 4a plus a, which is 5a. And if 10 is equal to 5a, that means a is equal to 2. It means that b is equal to negative 2. And c is the same as b, so c is also negative 2. So now I know what all these pieces are. And I can go back and drop them into my partial fraction decomposition. That was a over x minus 1, so that should be 2 over x minus 1. And then it was bx plus c, which is negative 2x minus 2, divided by x squared plus 4. So we have our a over x minus 1, and then our bx plus c over x squared, just looking at the part in yellow, the bx plus c over x squared plus 4. And this is what I want to be integrating instead. And furthermore, to integrate this, I really should break up this final fraction. So I can say I want to integrate this 2 over x minus 1. But then here I also want to integrate, let me actually bring the minus in front for each of these. It's probably reasonable to do that. I can say minus, and then I'm going to split this up about the numerator. There's no other way to. 2x over x squared plus 4, and then I can say minus 2 over x squared plus 4. And I want to be integrating these as 3 separate fractions. Well, let's see what we can do. Now, for this very first one, I can integrate it right away. So 2 over x minus 1, that's going to integrate. It's going to give me 2 natural log absolute value of x minus 1. For this next one, this middle one, I can integrate this. Let me put the minus sign first, the subtraction symbol between them. I can integrate this using a u substitution. So here we'd say, let's let u be equal to x squared plus 4. Du is 2x dx. And I have the 2x on top already, so this becomes the antiderivative of 1 over u du, which gives me natural log absolute value of u, plus a constant, but I'm going to deal with that at the very end, of course. And then all I have to do is back substitute. So that's going to give me natural log absolute value of x squared plus 4. So I can take care of that middle one with a u sub. That's going to give me natural log absolute value of x squared plus 4. But now this last one here is going to be a bit tricky. Well, let me actually write that minus sign first, and we can focus just on where we're integrating. So here I have 2 times 1 over x squared plus 4 that I'm trying to integrate. And I can leave that 2 in front and integrate this way. And this hopefully it looks familiar. This is going to be related to an arctangent form. If I had the antiderivative of 1 over x squared plus 1 dx, this would give me arctan of x plus my constant c. The problem is that it's not x squared plus 1, it's x squared plus 4. So I do have to change that. So here I could say 2 times the antiderivative of, and in the denominator, I want to factor out a 4. And I can do that, but to compensate, I need x squared divided by 4 plus 1 dx. It looks a bit funny, but if I distribute this back through, 1 times 1 is 1, of course, but then the 4 times x squared plus over 4, sorry, the 4 times x squared over 4, the 4's cancel, and then the 4 times 1 gives me the 4 back. So it's just kind of a funny way to write this algebraically, but I can go a bit further with this. If I want, I can bring that 1/4 out. 2 over 4 gives me 1/2. And I have the antiderivative of 1 over x squared divided by 4. I can actually write that as x over 2 quantity squared plus 1 dx. And from here, I'm still going to want to work with a u substitution. So here, I would go and say, let's let u be equal to x over 2. Then du is 1/2 dx. Or if I solve for dx, then 2 du is equal to dx. And I can rewrite this as 1/2 the integral of 1 over u squared plus 1, and dx can be replaced with 2 du. Now the 1/2 and the 2 are going to cancel, so I'm really just left with the antiderivative of 1 over u squared plus 1 du, which gives me arctan of u plus my constant c, and then I can back substitute to get arctangent of x over 2 plus c. And I kind of ran out of room with what I was writing, so let me rewrite what I already have. But from the first piece, we had 2 times natural log absolute value of x minus 1. In the middle piece, we did a u sub, a classic one, to get minus natural log absolute value of x squared plus 4. Minus, we had to modify and do a u sub on this third piece to get an arctangent form, and this gave us arctangent of x over 2, and then plus our constant c. But hey, we did it. So hopefully that feels good for you, feels great. Partial fraction decomposition, definitely one of my favorites. What a wild ride. No matter where you are and what you're doing, I want you to remember to always keep learning, keep dreaming, and follow your heart. And hey, I'll be seeing you soon for another one of these daily problem sets. Until then, make sure you take care of yourself. And I will see you next time.